Deform. Um, so we've been doing principal stresses. So let me just do a last little summary of principal stresses. Um, so principal stresses um, if you have to do it by hand, which you won't have to anymore in this class, but it does help with your understanding of what's going on. Um, Remember, the way that you do that is you you have this matrix, and you take the determinant of that and set it equal to 0. Um, in general, that means solving a cubic polynomial, which is troublesome. But when you solve a cubic polynomial in general, you get 3 roots. And those roots are your principal stresses. Um, and then one by one, so let's say this is the first step. And then the second step is one by one, plug in those principal stresses. And you're going to solve the equation sigma xx. We got to write this thing again. Sigma xx minus lambda, sigma xy, sigma xz, then sigma xy, sigma yy minus lambda, sigma this is sigma yz, sigma xz, sigma yz, and then sigma zz minus lambda. Okay, and we're going to take that matrix, multiply it by nx, ny, nz, and set it equal to the 0 vector. We're doing this one by one, so in each case, we're going to find the eigenvector that corresponds to each eigenvalue. Okay, so and remember that each of these is plus or minus. And those define the coordinate system orientation. Okay. Well, in this class, you won't have to do it by hand. So what do you have to do in your calculator? So first, you're just going to go, not all of you use this command, but whatever program you're in, just use the eigenvalues command on your stress tensor. I'm just going to put it in as a tensor instead of like that. So, and then second, do the eigenvector command on that same stress tensor, and the orders will match. So, for example, the first eigenvector you get from your eigenvalue calculator is going to correspond to the first eigenvalue you get from your calculator. Okay. This way of doing it by hand gives you a better sense of how what these things all mean and stuff, but this is what you're going to do for the rest of the class. Okay. Anybody have any questions left over about principal stresses?
Did you say if we use Wolfram alpha, it gives us like the unit vector, so we have to divide by the...
Yeah, it does not give you the unit vector, right? So you have to divide by the magnitude yourself. So, bummer. But actually, Wolfram alpha will do that calculation for you too. It just doesn't do it automatically for some reason.
But how do you get to do that?
Let's find out together. So just type in normalize, I guess. Is that right? Normalize.
If you hit like math input, you can get like the 3x3 matrix. You like just type in matrix into that.
Okay.
Go to the bottom. You see like
here, this will work too, right? So, okay, so if you put in 6, 2, -1, I don't know why I had to change that first one. So those are the answers, and I guess we want the approximate form, so that'll give you the decimal. Okay, so if you go eigenvectors, okay, so if this is our stress tensor, well, let's make sure that we need one that's symmetric. This one, so 2, 2, 1, and then this needs to be 3, 1. I think that's symmetric now. Compute. Why did I want to make that symmetric? Anyone remember? Before I got the eigenvalues? Anyone? That's supposed to be like the Ferris Bueller guy. The who Smoot, Holly, Bill. Did it help? No. Okay. So what would have happened if I would have put a non-symmetric matrix into that eigenvalue calculator? Yes, exactly. You get complex roots in general. So we don't want that. So I put in a symmetric matrix and then you get all real roots. So these are the three eigenvalues and these are the corresponding eigenvectors. And now I can take one of these. You might have to do it by hand, I suppose. It doesn't seem to want me to copy and paste that, but we got 0.833, 0.644, and 1. Okay, so I'm going to go to unit vectors. And I'm going to type in I want to do it. I just had it. What happened? Oh, here we go. Okay, so I'm going to go 0.833.
Oh, you just want the normalized one? Yeah, if you type in like the vector on the top, on the very top in the search bar, it just like brings you a bunch of stuff and then
oh yeah, really?
It gives you the normalized vector.
Oh, okay. So I want the normalized version of this. I'll compute it. And it didn't do it.
Is it the result or not?
Oh, it's this. Yes. Yes, yes, yes. The result. So, yep, it did it for me. Okay, any other questions about principal stresses or corresponding principal coordinate axes? So the eigenvalues are the principal stresses. The eigenvectors are the coordinate system axes of the principal coordinate system. And these are, of course, plus or minus. You know, I keep trying to remind myself to say that. So, you know, if you're really trying to make a coordinate system out of these, you're going to have to adjust the positives and negatives so that it's an acceptable coordinate system. Okay, so now we are done with stress and strain. We're done with the relationship between stress and strain. So now what we're going to do, like almost entirely, so almost all of what's left, which is a lot of this class, you know, is calculating stresses in specific loading situations. Calculating the stress in specific loading situations. And then so for a certain kind of beam, a certain kind of setup, you know how to calculate the stresses at a point in that beam. And then once you do that, you can do all these other things that we've been doing. You can calculate the strain at that point. You can calculate how that stress would transform into a different coordinate system. You can calculate what the principal stresses are. So all that stuff we've done, we can still apply. But what we haven't done yet is calculate any stresses in actual loading environments. You know, so that's what we're going to get into now. This will depend heavily on Saint Venant's principle. This is the other kind of principle than the principal stresses. That's one, you only get so many chances to look smart to people. And one way of doing that is using the correct form of principle. Principal stresses is like the principal of your school, like pal. The principal of your school is your pal. And a principle is like an idea or whatever, and that's this kind. Okay. And here's what Saint Venant's principle says. As long as you don't consider points too close to the loaded face, the stresses are the same for equipolant systems. I'll draw you a picture of this in a second. Okay, so for example, if you have a beam like this that's loaded by a point force here and a point force here, and you have another beam that's loaded by a distributed load here and a distributed load here, and those distributed loads come to a total of F. Okay, those aren't identical, but they're equipolant. Though that distributed load is equipolant to that point force. Okay, so what would happen when you apply these forces? Well, this one, if I exaggerate the deformation that would happen, would have an especially big deformation where that point force is applied. Okay. Whereas this one, since that's a uniform distributed load, would just stretch uniformly along the whole face. And it's clearly obvious from these drawings that those deformations and those stresses are not the same. But if you ignore the stuff that's happening close to those faces that are loaded, so you just accept that you don't have a way to figure out what's happening right next to those faces. Damn it. Then everything that's not crossed out in red, those stresses are going to match. Okay, so the differences in those stresses are only happening close to where the loads are applied. Okay, and so in this class, we're going to a lot of times do sort of idealized versions where we're replacing a loading environment with an equipolant set of loads. That's okay as long as we just remember not to trust our values right next to where the load is happening. Okay. Then the next question is, how close is too close? So how far away from the loading face do you have to get before you trust the values from your calculation? And just a good rule of thumb is about the longest dimension of the loaded face. Okay, so in the example that I drew here, where I drew these regions to ignore, that is somewhere in the ballpark of the longest dimension of the loaded face, right? And so everything in white, we can trust those results. Those are good results, okay? If you did a more careful calculation of the stresses, you would see that in these two cases, everything matched up almost identically inside in those white regions, okay? But what about something like this? So let's say that we had something like that, and we have a point force here and a point force here, and then over here, we want to, in order to do this calculation, we want to replace this point force with a uniform distributed load. Well, now the greatest length of the face is bigger than the distance between the two ends. So in this case, you can't trust any results. From uh, from using an equipolant system. Okay. Anybody have any questions about that? So I'm going to try to bring that up from time to time. Like, where do we trust these results? Where don't we? Usually, what's going to happen is we're going to have cases where there are point forces applied or a certain distributed load applied, and we're going to substitute a simpler distributed load profile, like a uniform distributed load, because it makes the calculations easier. Okay. So St. Venant's principle. All right, and the first type of calculations we're going to do, where we're going to have a specific loading situation and we're going to be able to calculate the stresses, is members in pure tension and compression. Um, and the calculation of the stress in members in pure tension and compression is going to look familiar from the tensile test. So if, let's say that we have a member like this, and we put it in pure tension, I could have those going the other direction, and then it's compression. And I'm going to use a coordinate system, sort of like the one that we use in the tensile test. So the x-axis is that way, y is this way, z is this way. Then the only non-zero stress is sigma xx. And so that's the normal stress along the x-axis. And that value is equal to the force divided by the cross-sectional area, where this red is the cross-sectional area. Okay, so I mean, when we do the tensile test, that's how we calculate the stress, and that's how we do it again here. So so let's see this in a simple example first. So let's say that we have a bar like this with 5,000 newtons of force applied in compression. I'm going to use a coordinate system like this. Sigma xx. This is in compression. When it's in tension, that force is positive. When it's in compression, that force is negative. So we have negative 5,000 divided by, I didn't give any dimensions. Let's say that this radius is 1 centimeter. So 0.01 meters. And so the cross-sectional area then is going to be pi times 0.01 squared. And so that comes out to be negative 1.59 times 10 to the 7 pascals. And this negative is because it's in compression. So the stress tensor in this coordinate system is negative 1.59 times 10 to the 7, and then zeros everywhere else. What's the maximum shear stress in this bar? Well, to calculate the maximum shear stress, you first have to get the principal stress tensor. How do we get the principal stress tensor from this? That's how you do it in general, but in this case, I mean, think of the definition of the principal stresses. You know you have a principal stress tensor when there are no shear stresses. So this is already a principal stress tensor. And so we can skip that step here. Okay. So this is already principal. And that means that we can calculate tau max as the maximum principal stress, 0, minus the minimum principal stress, 1.59 times 10 to the 7, divided by 2. And so that is 0.795 times 10 to the 7 pascals. Okay. Any questions about that? So when does, what are some cases where you would have members in uniaxial tension or compression like this? One important example is trusses. So remember that a truss is a structure where every member is either in tension or compression, and that's all. So every member is in pure tension or compression. The people who took statics from me, we didn't spend a ton of time on trusses. I think probably people who took statics at other places spent a bit more time on trusses. But let's first just remember what the definitions are. How can you identify something as a truss? And then we'll go into calculations. So can anyone remember any of the requirements for a structure to be a truss? The any forces, so there can't be any couples applied. Any forces have to be applied at the joints. That's right. And there's like one other big one that goes.
Of the bodies themselves.
Yeah, we have to be able to neglect the weight of the bodies of the members. Exactly. So here's how I'm going to say it. So for something to be a truss, every member has to be a two-force member. And that requires those two things that you just brought up. The first one is that the weight has to be negligible for each one of these members. And second, all forces have to be applied at the joints. Okay, so if these conditions are met, and those are pretty stringent conditions, so you have to ask yourself every time you see a structure whether these conditions are met or not. But if these conditions are met, then you're going to treat every member like a cable in tension. Second, use Newton's second law at each joint. So there's no moment equation here. We're going to treat each joint like it's a particle and just do particle kinetics or particle statics. And then third, negative tension values mean compression. Okay, so we'll start with a really simple one. So let's say we have a triangular shape. And this angle is 70 degrees and this angle is 70 degrees. And we have a 2,000 Newton force applied like that at the joint. The length of each one of these members is 1 meter. And the question is, what's the smallest cross-sectional area A that we can use so the maximum shear stress stays below 1 times 10 to the 7 pascals? Okay, you can imagine how this would be like an important design question. I mean, you have this structure that has to support a certain load, and you just want to know what's the minimum amount of metal that you can use for this to be safe, you know? I'm going to call this member 1, this member 2. The joints, I'll call this A, B, and C.
Could there also be an example where we keep the metal length fixed and just change the angles instead?
Yeah, right.
But an example where we're just like keeping the joints fixed and then
yeah, we're saying the geometry of it is all the same, except we're just trying to figure out how thin these bars can be. You know, what's the cross-sectional area? How small can we get that down? So I'm going to do a free body. Okay, well, first I said, whenever you see a structure, before you blindly start applying the rules of trusses, you need to ask yourself carefully, does this meet the requirements of a truss? I didn't give any masses. We're going to assume we're neglecting that. So, okay, no weights. And then all the external loads are acting at joints. And so this is fine. We can use the truss simplification here. Okay, so now I'm going to go for free body diagram of that joint B. We're going to assume that member 1 is a cable in tension. So that would be pulling on it this way. I'll call that F1. Member 2, we're going to treat like it's a cable in tension. So that would be pulling on it this way, and that's F2. And that 2,000 Newton force is also applied to that joint. So 2,000 this way. That's all the forces that are applied to that pin. And so now I'm going to go to Newton's second law. And we have, so F1 times a unit vector in the direction of that arrow, which would be negative 0.342, negative 0.940. Plus F2 times a unit vector in that direction, which would be positive 0.342, negative 0.940. Plus that 2,000 Newton force vector. So that's 2,000 in the positive X, 0 in Y. And this adds up to be the 0 vector. And so we have two equations, negative 0.342 F1 plus 0.342 F2 is equal to negative 2,000. And the second equation says negative 0.940 F1 minus 0.940 F2 is equal to 0. You can see from the second one that F1 and F2 are just opposites of each other. Substitute that in, and what you get out of this system is F1 is equal to 2123.8, and F2 is equal to negative 2923.8. Okay, so which one of these is in tension? F1 is in tension because its tension is positive, and F2 is in compression because it's negative. Okay. And now I'm going to go through a calculation for each one of these of what the maximum shear stress, because we want to keep that maximum shear stress below the value that was given. Okay, so let's go to member 1. The stress tensor is, member 1 is the one that was in tension. So this is 2923.8 divided by a cross-sectional area A, and then zeros everywhere else in the stress tensor. And that is a principal stress tensor. So we can use that to calculate the maximum shear stress. So tau max is equal to 2923.8 over A minus 0, all divided by 2. And so the maximum shear stress is 2923.8 divided by 2A. Are you with me on that? And then, so now we're going to set that equal to the maximum that we want that shear stress to be. So 2923.8 divided by A is equal to 1.0 times 10 to the 7. And, yes. Thank you. And so we have that A is equal to 2923.8 divided by 2 times 1 times 10 to the 7th. And we get an answer of 1.462 times 10 to the minus 4 meters squared. So if we have somehow figured out that the start of our concern about this thing breaking is at a shear stress of 1 times 10 to the 7th, then we know that we don't want the cross-sectional area to be any smaller than that. Okay? And then for member 2, it would be a similar thing. Can anyone off the top of your head just figure out what the answer is going to be here? Yes, exactly. Exactly. It's going to be the same. So this time we have a stress tensor of negative 2923.8 divided by A. Zeros everywhere else. So tau max is equal to 0 minus negative 2923.8 over A, all divided by 2. And so we get the exact same thing again, 2923.8 over 2A. And so we get the same answer for member 2. Any questions about that? That was given as part of the problem. So I just said, we know what this metal can withstand, and we don't want that stress value to be any bigger than that. And so let's see how much material we have to use. And if we use more material, then the stress is going to be smaller than that. Okay. Okay, so let me write one of these up here and give you a chance to work through a truss calculation. So let's say that we have, so this is going to be an equilateral triangle. Doesn't look like it, but it is. And we have a roller over here. Crash. So all these angles are 60 degrees. And let's say we have a 1,000 Newton force here and a 1,000 Newton force here. And the lengths, just to make the math easier, we'll make them all 1 meter again. And the cross-sectional area, we'll say, is 1/1000th of a meter squared. And we want to calculate tau max in each member. Okay, so before we get into the calculations, we have to think about whether this is a truss. Is there any mention of mass or anything? Do we have to worry about the weights of the members? No. And then are all the external loads applied at pins? Yes, so we can treat this as a truss. And just so we're all our numbers look the same, let's call it 1, 2, 3, and A, B, C. And okay, see if you can work through this calculation, and then after I give you a little while, I'll go through it. So first of all, I'll go to a free body diagram of A. So we have F1 like that, F2 like that, and then we have the unknown reaction force vector. I'll call that RA. That's the force that the ground applies to the pin. And so Newton's second law says RAX, RAY plus 0.5 F1, 0.866 F1, plus F2 0 is equal to zeros. Any questions about that one? What?
I.
Where's
What is
where's I?
I?
What is? She's asking what is R? What is your
Oh, R. Oh, okay, sorry. I thought you said I. R is the force applied to the pin by the ground. So that's the reaction force with the ground. And then we'll go to B. So we have F1 going this way, F3 going this way, and 1,000 this way. So Newton's second law says negative 0.5 F1, negative 0.866 F1, plus 0.5 F3, negative 0.866 F3.
Or what would be the angle that you're finding the cosine of, or the sine, the cosine sine of each of those?
This would be, yeah, so
For B, I got A, because like F1's really easy.
Yeah.
Up at 60-degree angle.
Well, one way you can think of the first one here is it's just the exact opposite of the one from as the 60-degree one from the first.
Okay, so just going.
Yeah, so you're just multiplying it by -1. And then the second one would be 120. And then we have plus 1,000, 0. And that's everything. And then we'll go to C. There is an upward force from that roller. So I'll call that RC. And there is the force F2 pulling this way. And the force F3 pulling this way. And then a 1,000 Newton force this way. So we have 0 RC plus negative F2, 0, plus negative 0.5 F3, positive 0.866 F3, plus negative 1,000, 0. And we have 1, 2, 3, and the 3 members is 6 total variables, 6 equations, so we can solve this. Does anyone have answers for these yet? Let's, you are just doing it all by substitution. Let's write out a augmented matrix and do it that way. Okay, so for variables, I'm going to say F1, F2, F3, RAX, RAY, and RC. And then these are the constants. My equations 1, 2, 3, 4, 5, 6. So from equation 1, we have 0.5 for F1, 1 for F2, and 1 for RAX. For equation 2, F1, we have 0.866. And then for RAY, we have 1. For equation 3, F1, we have negative 0.5. F3, we have 0.5. The constant, when you get it over to the other side of the equation, is negative 1,000. For equation 4, F1, we have negative 0.866. For F3, we have negative 0.866. And nothing else. And then for equation 5, F2, we have negative 1. F3, we have negative 0.5. And then the constant, when you get it to the other side of the equation, is positive 1,000. In equation 6, F3, we have positive 0.866. RC, we have 1. And that's it. So could you take a minute and do negative 500 for F2? And negative 1,000 for F3. All right, yay. So take 2 minutes from here and calculate those maximum shear stresses in each one of these members, okay? So, okay, we have these forces, and now we're told that the cross-sectional area of each of these is 0.001. So for member 1, that sigma xx is 1,000 divided by 0.001, which is 1 times 10 to the 6 pascals. If you did a stress tensor, it would just have this and zeros everywhere else, which means that tau max would just be half of this. So 0.5 times 10 to the 6 pascals. For member 2, the tension in that member is negative 500, compression of 500. So sigma xx is negative 500 over 0.001. So 0.5 times 10 to the 6 pascals.
Still negative though, right?
Negative, yep.
Negative.
Thank you. Yeah, that negative is super important. Thank you. Don't drop that. But it will drop from the tau max because of the way that equation works. So tau max will end up being half of this. So 0.25 times 10 to the 6 pascals. And then for member 3, sigma xx is negative 1,000 divided by 0.001. So that's negative 1.0 times 10 to the 6. So tau max is 0.5 times 10 to the 6. So if you built this structure and you wanted to know what member you were concerned about breaking.
Members 1 and 2.
Well, those are the ones where it's going to be longest to get to your maxed house. It would actually be member 2 would be the one that you're most concerned about.
Can you see that?
Well, yeah, the one with the lowest. This is the one with the lowest maximum shear stress, and so that's the one you're most concerned about breaking in this configuration. Number 2, because it has the lowest. It's, yeah, right. Okay, that's all.